Okay, so last time during the class that I teach, we ended at this point. So we made a vector of numbers and we got 8675309. We searched for 999, blah, 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 which is obviously not in this list. We called the binary search function, which returns an integer. So it returns the index of the element searched for and -1 if it's not found, as it says there. Let me add to that precondition there. Precondition array must be sorted. And if we save, then that appears there. Array must be sorted. Okay. Otherwise, the algorithm is not guaranteed to succeed. In fact, it's very unlikely to succeed. The binary search algorithm, the function definition is here. We include a Boolean variable for whether or not we find the search value, which is of type T in this case, because we're using templates. So we can have vectors of strings, integers, doubles, Booleans, etc. Or more complicated types like a car class, for instance, objects of a car class. We have a while loop and we do a comparison operation. And if that comparison evaluates to false, we shift the last, middle, and first positions that we start our search at. Okay, to put it very briefly. I believe I've yet to make this simple point that binary search is generally faster. Well, let's say, generally faster than sequential search. And an assignment that I have posted is asking students to confirm that that is indeed the case. So here, I say generate an array of even numbers from 0 to 50. And let's just look at this output. So here's an array, a screenshot of output of even numbers from 0 to 50. If we search for 24 using sequential search, we say, is 0 24? No. Is 2? No. Is 4? No. And we move all the way on until we get here. So I say guesses here, but I should really have called this comparisons, total number of comparisons. So comparisons in the case of sequential search is this comparison right here. Okay. So the binary search got very lucky in this case because binary search starts at the middle index. And can we see that in the code? Yes, it is right here. So the middle index is equal to first plus last divided by 2. So just to give some context to these, first is set to 0 initially when we step into the binary search function. Last is the size of the list minus 1 because we started counting at 0. So if a list has 5 things in it, then last is equal to 4. So in the terms of the example we gave, we got 1, 2, 3, 4, 5, 6, 7 elements, and 7 plus 0. Yeah, let me, okay, so got interrupted just then, so threw off my track, of course. Right, so we had 7 things. We have 7, the size of this list. If we were to say cout nums.size, it would print 7. So last is equal to 7 minus 1, which is equal to 6. So 0 plus 6 is 6. 6 divided by 2 is 3. So the middle index gets set to 3. So in this case, when we step into this loop, we'll say is list at, so what is this list? In this case, it is called nums. So we ask the question, is nums at index 3 equal to the search value? What is the search value in this case? It is this value. All right. So 0, 1, 2, 3 is 5 equal to 99999. No, it's not. So we evaluate the else if. And at this point, I think it's best to go ahead and set a breakpoint. Oh, My mistake. We did sort that list before. So the third index wouldn't be 5 unless that's a coincidence. The third index would be 0, 3, 5, 5, 6, 7, 8, 9. 1, 1, 2, 3, 4, 5, 6, 7. Okay, I think I did that right. So the third index would be 6 here. Sorry about that. I was thinking about sequential search. So we do sort this, and we demoed the sort function last time. All right, let's set a breakpoint. That's the way I should have done this instead. Binary search is generally going to be faster, and we can see that point here. It'll take 12 searches to find the value 24, and the value 24 gets found immediately with binary search because in this it happens to be the middle index. If we search for 8, it will take more than 0 searches to find 8 because 8 is not in the middle of this array, but still, well, in this case, the sequential search and the binary search tied. The same number of comparisons were needed. Now, searching for 44, we take 2 guesses for binary search. So binary search is faster than sequential. How much faster? That's a good question, and we're eventually going to get at that. The binary search is called big O log n. Okay, which is better than big O in linear time complexity. Okay. Let me hold off on getting at that, and let's step through with a breakpoint enabled and look at the values of local variables. So step, say, okay, step. All right, and what is the list of sorted things? It has size 7, as I mentioned earlier, and it's 0, 3, 5, 6, 7, 8, 9, because it is Jenny's phone number except sorted. All right, so we understand what this variable is. This is uninitialized, 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 and this is about to be initialized, and it auto initializes to true, evidently. Okay, so we step, and that's going to change to false because that's what just happened. That's the instruction that was just executed. 0, you see the red updates here. This is very nice to see. Okay, middle is uninitialized, so it has this value, but we're okay at the moment. It's not going to be a problem that this is an uninitialized value because we're not attempting to use it yet, but we are about to change it. So is first less than or equal to last? Yes, because 0 is less than or equal to 6. Found must be false in order to enter this loop, and it is. If this was true, a compound condition, let's not go back into that stuff from Programming Fundamentals 1. Okay, so we step into the loop. First is 0, last is 6. The middle is about to get updated to the value 3. Okay, and it did. And we ask the question, is the list, which is this list right here, is the list at the middle index, which is 3, equal to the search value, which is at the moment uninitialized, the 141 blah 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 blah. Interestingly. Oh, okay. I actually overflowed the integer type here, so that's why this value is a weird value. Let me use something that doesn't overflow the integer data type and rerun this program, just so we don't get confused by that. Now the target value is correct. That's kind of an interesting thing to see. Okay, now search values comprehensible, something that we passed in there. No integer overflow error. So is 99,999 equal to 6? No, it's not. So this, we will not set found equal to true, of course. We evaluate the else if. So is 6 greater than this? No, of course it's not. So we aren't going to do this operation. We're not going to update the value of the last index. Instead, we execute the body of the else because there is no it should be clear why we do that. So we're about to change the position of first. We're going to set it equal to middle plus 3. Middle is 3, excuse me, middle plus 1. Middle is 3, 3 plus 1 is 4. So 4 is about to change to 4. And what does that look like in terms of a search algorithm? I could draw this on a tablet, but we know that since the array is sorted and the middle value is less than our search value, we aren't going to look at this half of the array anymore. We only look at this half. We only search through that half of the array for our value. Of course, it's not there, but if this, and we could see that with only 6, a small array, we can see that easily with human eyes. But if this were a more realistic big data type scenario with 100,000 elements, it would not at all be obvious necessarily that we didn't have a certain value. We could do some fancy things like if the max value in the array is, let's not get into that. Okay, and yeah. Okay, so first is going to get updated. So it gets set to 4. Now we come back and is 4 less than 6, less than or equal to 6, which is still the position of the last index. Yes, it is. And found is still false. So we do step into the while loop again. First is 4, last is 6. 4 plus 6 is 10. 10 divided by 2 is 5. So middle gets updated right now to 5. Okay, 5 is the list of things at the 5th index, which is 8, equal to the search value. No, it's not. So we're not going to set found to true. We evaluate this instead. And what was it? It was 8. So is 8 greater than 99,000, blah, blah, blah? No. So we execute the else again. We once again modify first. So first gets set to 6. And now our search range is going to be we're going to examine the last element. Okay. So is 9 equal to 99,999? No. Okay. But is first less than or equal to last? It is equal to last. So, okay, so we will step inside the while loop, right? And it's going to be the final time that we step into it. So first is equal to last. 6 plus 6 is 12. Divided by 2 is 6. So middle is going to get set to 6. So we will have a case where first, last, and middle are all the same. Okay, let's see how that goes. 666, isn't that cute? So is is 9 equal to 90, the search value, this guy? No, it's not. Okay, is 9 greater than that value? No. Okay, so now we update first and we say first is equal to middle plus 1, middle is 6, 6 plus 1 is 7, so we're going to set first equal to 7. Okay, so is 7 less than 6? No, it's not. So our while loop is done. And we set found equal to false outside of the loop, and found is false. So we do not return middle. Instead, we return -1. Okay, so that -1 means not found. So that's one example of stepping through line by line through the binary search algorithm. If we want to, let's test something that is in the array. And this is going to be what is called a best case scenario data point for this binary search algorithm, because it's going to take the minimum amount of time. So this will be kind of nice and refreshing. So we found the index, founded index 3. And I didn't mean to remove my breakpoint there, so let's do that. Let's reset that. So we step into the function definition. Let me remind people of how this button is working here, these buttons. If I say step over, it will step over that function definition. It just stepped over, and their cursor is right here at the close brace. So that's what it means to step over right there. steps out of the main function, but if I want to see the details of this function, I click step into. Okay. All right, no changes from last time. Okay, still no changes from not last time. But now, list of thing, middle is equal to 3 still. You can see I'm hovering with the mouse here. So list of things, so it's 6, and the search value is 6. So this will set found equal to true. And then we'll come to the next iteration of the while loop. And is it the case that we have not found? This is true. I didn't say that well, but we're not going to step into the while loop. We're going to say if found is true, and we return middle, and middle is equal to 3. So, all right, that's the best case scenario for the binary search, the middle element. All right, now we actually already did one possible worst case scenario, which is the value is not in the array at all. But another scenario which is not optimal is it's a bad case scenario is the value 0. So let's go one more time through the algorithm. Target value 0 will be found, and it will be index 0. Maybe we make this 9 instead, just so we don't confuse the target value with the index, because 0 has the index 0, which might be a little confusing. 9 has the index like 7 or 6 or something. 6. Okay, so if I step over, it's going to print that we found the number 9 at index 6. But if we rerun and we step through the algorithm line by line, no changes to these guys. This will not evaluate to true because our search value is 9 and the middle element was 6 here, right? Yeah, index 3 has value 6. So, okay. So we step. And is this true? Is 6 greater than 9? No. So that doesn't get executed. The else gets executed. We update first to 4. Okay. For 4 is, of course, less than 6. We update the middle index. And now what is middle? Middle is 5 and 8. So is 8 equal to 9? No. Is 8 greater than 9? No. So once again, we update first. Okay. I think at this point, it's fairly clear how the algorithm's working. So I'm just going to stop debugging. And I'd like to get back into big O notation because that is algorithm analysis, and a decent thing to do at this point would be to make some plots, x versus log of x. Okay, so the log of x, the green curve, increases more slowly than the blue curve. So a computer scientist would be plotting time versus the number of x elements. So the execution time is the y-axis, the x-axis is the number of elements in the array. So the number of elements in this array is 1, 2, 3, 4, 5, 6, 7. And it takes a certain amount of time for a binary search algorithm to execute. So I showed the timing results for the sequential search. For binary search, I would like to use the more typical approach in a computer science class, which is to keep track of the number of comparisons. Okay. So every time we do a comparison, we increment the comparison count. make it print this. And I want to automate this process and make it quicker. Let me make a new project. I'd like to write a function and test use random number generation. And it's gonna be a while, and I don't want to make this a really long video, so let me just do that and then resume the recording later. Okay, so in the search algorithms header file, I went ahead and pasted this function definition that I've written before, generate n random numbers between 1 and n. So that's in the header file that I have included. So instead of using this case, I will comment this out and keep the variable name the same for now at least. And maybe we say auto nums equal generate in random numbers between 1 and n. Let's say 100 random numbers, and let's make a variable for that. So that if I change it in one place, I don't forget to change it in other places. Okay, so we've got random numbers between 1 and 100 now, and then we're going to sort those numbers and we're going to search for a target value. And yeah, I guess we just keep it at 9 and see what happens. Yeah, I think this will work okay. Okay, so search algorithms.h, I have errors there, so let's see. On line 11 at the earliest. Uh, random uniform, not a member of namespace standard, so pound include random here to be able to use this. I remember not using the rand function anymore. It has certain deficiencies, so that'll get rid of some of those errors, maybe all of them. Okay, so performed 7 comparisons and did not find the value 9. So it's a little bit interesting that we didn't find it, because the random number generator should generate most of the numbers between 1 and 100, but if we rerun this, I think we will find this value. It's not a problem that we didn't find it. Took 7 searches, and then we found it on this second try. But let's print those numbers after we sort them. Print back, I think, was the name of my function, and I think it's in the algorithm, the search algos header file. Okay, and so we're searching. Let's also print the search value found. Search value. What do I call it? Target value. Okay, is 9 in here? Yes, it is. And it is at index 0, 1, 2, 3, 4, 5. So that's right. And it took 4 comparisons to find this, which is, in a way, it's fairly impressive. Okay. So what's a worst case scenario for this data set? Like 100, something that's not in the array, 101 Dalmatians. So it's 7 comparisons. All right, let me write that number down. I'll just write it down in Notepad. I was considering doing something else there. Okay, there's like a table of values. So for 100 elements, it took 7 comparisons to find the worst to, that was the worst case scenario. Can it get any worse than that? A greater number of comparisons? No. All right, I hope what I just said just makes sense without trying to go into greater detail on it. Let's make 1,000 random numbers. Maybe we don't go that far yet. 1,000 is going to be a lot. It's okay, I suppose. Won't be too unpleasant. And once again, let's check for something that's not going to be in there, which is 1,010, because of the way this function is defined. Okay, so we printed 1,000 numbers and it sorted them. So okay, and we searched for 1,010, which is not there. Okay, and it said it took 10 comparisons. So 1,000 took 10. All right, and now if I go up to 10,000, and I'm not going to print it anymore because it'll take a while. And 10,000, that number is not between 1 and 10,000. It's going to be a worst case scenario. Took 14 comparisons. 14. Okay, let me make this a little bit more suggestive. We've got some data points here and we could plot these and they would make a certain shape. 32. And I'm going to generate, and I'm going to look for the value 34 because that's going to be, well, it's going to be the worst case performance. 6. So 32. 6. Okay, 64. I'm going to make this 65 so it's out of range. So it's 64. Okay, 7 comparisons. 7 comparisons. So 64 got 7. And now I'm going to do 128 and search for the value 129. And we do 8. Okay. We probably get the point at this point. What I'm trying to show here. And let's move that 100 up. So do we see a pattern here? 2 raised to the power n, 2 raised to the number of comparisons. Yeah. 2 raised to the number of comparisons is equal to n. Okay. Another way of saying this is that the binary search algorithm has big O log base 2 of n complexity. So the number of complexity is the number of operations an algorithm has to perform in order to do its job. So the comparison is generally regarded as the most expensive operation that we do here in this algorithm. So we have some statements that initialize, but the main work of this algorithm, what will have the most overhead is these comparison operations. Okay. So, I mean, to put it really simply here, or to put this in a different context, big O login. This is a very classic thing to go. All data structures and algorithms classes mention the binary search algorithm and how it's fast. It's generally fast. A question that should naturally occur to us at this point is to say, is it the array must be sorted? How expensive is it to sort? Um, I just called standard sort on 128 numbers. A human could not do this particularly quickly. So if we print before we sort 128 random numbers, and you're given this list of numbers to sort, maybe you are not a happy camper. So if we do many searches, if our application, whatever program we're writing, like Amazon, the website or the app, enables you to perform as many searches as you would like for tennis shoes or whatnot. So it definitely is worth it in that application to sort items in a database. So we should wonder how expensive it is to sort. What is the complexity of a sorting operation? And are there certain sorting algorithms that are better than other sorting algorithms? And the answer to that question is yes. And that's a decent stopping point for this video. But just to see if I did anything particularly interesting in my slides here. Just scrolling through my slides here. There's sequential search business. Talked about best case scenarios, worst case scenarios. We sort of did pencil and paper approach. Okay. There's this cute comment from father of algorithms or whatnot, Donald Knuth. Best case, worst case, comparisons, not guesses. That's a silly thing that I did in the past. Okay, all right. Number of guesses, number of elements, which is something I just showed. Okay, so I was demonstrating a worst case scenario, but on average, the number of comparisons is big O log of 2, log base 2 of n divided by 2. Okay. And I haven't brought this up yet. If you supply a best case data point, the complexity is called big O1, which is called constant time complexity. Um, we'll encounter that again in the future, but if we plot 1, it's a constant line, so the time on the y-axis does not increase with the number of elements. So if you're always searching for the middle, if you call the binary search and you're always searching for the middle value in an array, that's always a best case scenario. So that complexity is called big O1 by computer scientists. I would rather call it big OC, like C is in a constant. I guess I closed my calculator quickly. So C is a constant, and you can drag this around to have different constant values. I would prefer to say big OC, but it's very much a thing in computer science to say big O1. Like 1 it doesn't change regardless of the number of elements. This is y equal 1 for people coming comfortable with algebra. Yeah, so is it worth it? There is a big O1 search algorithm, and it's related to what's called hash function. So that's it for the slides. on searching and algorithm analysis. So next, I'll be getting into next up in my modules is topic 1B, which is sorting and algorithm analysis. So we'll write a sorting algorithm. We already have used standard sort. So why reinvent the wheel? This is a good question, but sorting is a good, it's a good, fairly simple case for learning about algorithm analysis. Okay,